Hello, in this video I present my project titled Machine Learning for Financial Distress Prediction using CDS data and fundamentals. The objective of this project is to examine whether machine learning models can extract incremental predictive value from credit default swap spreads in combination with accounting fundamentals and equity market data. I will compare this to a simple heuristic threshold rule benchmark. I will first motivate the problem, then describe the methodology, present the main results, and conclude with a short demonstration of the code. Predicting financial distress is a long-standing challenge in finance. Traditional approaches rely mainly on accounting-based models built from historical financial ratios. While these models are intuitive and easy to interpret, they have important limitations. They are inherently backward-looking, they react slowly to changes in credit quality, and they typically assume linear relationships between variables. In contrast, market-based indicators, such as credit default swap spreads, provide a forward-looking assessment of default risk. CDS spreads aggregate information from many market participants and adjust quickly when firm credit conditions change. However, despite this rich information content, CDS data is often used in practice through very simple heuristic rules, such as fixed thresholds, which may fail to exploit its full predictive potential. Based on these limitations, the core research question of this project is straightforward. Does machine learning extract incremental predictive value from CDS data beyond simple heuristic threshold rules? The motivation is that CDS spreads contain rich, forward-looking, and nonlinear information, and modern machine learning models are specifically designed to exploit such structure. The hypothesis is that improved performance should come not only from using CDS data, but from applying more sophisticated models that can better extract signals from it. The dataset combines three main sources. Accounting data comes from Compustat North America, equity market data comes from CRSP, and CDS spreads are taken from Capital IQ. All data was accessed through the CEDIF research infrastructure at HEC Lausanne. After merging all sources, the final sample includes around 600 US firms and more than 28,000 firm quarter observations, covering the period from 2010 to 2023. Financial distress is defined as a binary outcome over a 12-month horizon, based on forward-looking CDS spread movements rather than actual bankruptcies. A firm is classified as distressed if its CDS spread increases by at least 50 basis points or by at least 25% over the following year. To ensure a realistic evaluation, the data is split in a time-consistent way. The period 2010 to 2020 is used for training, and 2021 to 2023 is used for out-of-sample testing. All features are built using only past information to avoid look-ahead bias. To answer the research question, I use an incremental experimental design. The idea is to separate the effect of model sophistication from the effect of adding more information. First, a naive CDS threshold rule, where higher CDS spreads indicate higher distress risk. This serves as the baseline. Secondly, I replace the heuristic rule with a machine learning model, XGBoost, applied only to CDS-derived features. This step isolates the gain from using a more sophisticated model while keeping the same information. Third, I use the same XGBoost model but expand the feature set by adding 10 selected accounting and market variables, choosing using SHAP values. This final step captures the additional gain from information expansion. This structure allows me to clearly measure how much improvement comes from the model itself and how much comes from adding more data. For the modeling step, I evaluate several machine learning models, including XGBoost, LightGBM, and Random Forest. These models are compared using the full available dataset to assess their overall performance and stability. Based on this initial comparison, XGBoost and LightGBM consistently show the strongest and most stable results. The comparison across models is discussed in the written report and summarized in Figure 1. For reference, I also include logistic regression as a simpler baseline model, which helps assess the added value of more flexible machine learning approaches. Although XGBoost and LightGBM perform similarly, I mainly focus on XGBoost in the report as it showed slightly more flexibility across different experiments. I will detail this choice in the code demonstration at the end. To ensure clean, reproducible, and realistic results, the project is implemented as a modular 15-step data pipeline. Each step performs a specific task, such as data loading, cleaning, feature engineering, or model training. A key focus of the pipeline is data integrity and temporal consistency. All pre-processing steps are applied using only information available at the time of prediction. The code is organized so that the main pipeline contains stable, prediction-ready steps, while additional analysis and robustness checks are separated into an experiments folder. This separation improves transparency and makes the workflow easy to reproduce. This pipeline structure ensures that results can be reproduced and extended in a consistent way. Feature engineering is designed to strictly preserve temporal integrity. All features are constructed using only information that will have been available at the time of prediction. For CDS data, this means creating lagged CDS spreads, as well as changes over 1 quarter and 1 year. In addition, I compute rolling volatility measures using past CDS observations. The same principle applies to accounting and equity market variables, which are also lagged and aligned in time to ensure consistency across data sources. This is essential in financial modeling, because even small look-ahead biases can strongly inflate performance and lead to misleading conclusions. Having explained how features are constructed and how temporal integrity is ensured, I will now briefly demonstrate the code execution and show where the main results and outputs are generated. Okay, so now we are in the link that I gave you in the mail. I'll send you in the mail. So here's my repository. So you can see here all the detail of my pipeline, experiments, output, etc., etc. So in the README, I detail in the setup how to clone it, install dependencies, and also the usage of to run the main.py. So let's do it together so you can see that it runs successfully. So first we will clean the repository. So I did it many times, as you can expect, so it will be really quicker than you. Here you have two options for the dependencies. So the first one is using pip, and the other one is using conda as recommended as from the TA. So I'll just activate it, but if you want, you can create the environment.yml to verify that it works. But normally, if you just activate it, you'll see that it works. So, and then I'll just Python 3 and main.py, just run the main pipeline. So now I'll just wait for the running time. So for me, the running time should be like 1 or 2 minutes, because I did it many times, as I said. But for you, maybe it will take about 15 minutes, I think, but not more. I have all the data in my data folder, so I don't use API or something to process data. So normally it won't take too much long. Maybe just for like tuning the models, or you can see in the step 12. I'll just show you here. Here is the model comparison. So as I said in my earlier slide, So I did the LightGBM, XGBoost, random forest, and logistic regression, as you can see, and I choose the first two ones because of the AOC, F1, precision, and recall that are best. And just the LightGBM, you can see the recall is really bad. Oh, it went, so I'll go down. The recall of the LightGBM is really bad, so that's why I choose XGBoost instead of LightGBM, even though it has a slightly more IUC, but yeah, XGBoost was more stable in all the metrics than LightGBM, so that's why. And then here we have the experiments folder that are running also. I also run the experiments, not only the principal pipeline. So you can see everything that I tried, and some things that I didn't keep, some things that I kept. But so you have the global ID and what I tried to see. For example, here it's the medium versus strong regularization for LightGBM. So even though I didn't choose LightGBM as my final model, and also I didn't report it in my report, I did all the same experiments that I did for XGBoost for LightGBM to see and compare them, and how they behave. So here you can see that my best model is the XGBoost with the top 10 sharp features and with the strong regularization, because as explained in my report, I had some problem with overfitting, and the regularization really helped me to 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 go by this. And then here you have the runtime. For me, yeah, as I said, it's quick. Then here's the detail. So my first 15 pipeline are the principle and core of my project, and then I did here's only the XGBoost experiments, but I also, for example, the 16 is for LightGBM, but here the 1B, C, D, E, F is the core experiments that I really put in my report and use. As you can see, all the pipeline and all the experiments successfully run. You can see the saved results are the same. The saved results path for each visualization and results. If you want, I can show you. For example, ls outputs. Okay, and then here you will have all the CSV if you want to go like CSV per CSV. But yeah, you have, for example, sharp values for LightGBM, for the XGBoost. You have the summary for data quality, CDS quality. It was also tough with CDS data because it's not really rich as like equity market data. And also I can show you this report. CD figures, and yeah, here it's all the figures that I have, and also you see here experiments. And if I say change CD experiments and ls, here you can see that in this folder experiment I have the figures that are related to the experiments. So here's the detailed code demonstration that for my project. Everything worked. So normally you will have the same results as me, and also it's the same as I shown in my written report. So thanks for listening, and let's go through the slides. Thanks for watching the code demonstration, and I will now briefly summarize the main result of the project. The key question is whether performance gains come mainly from adding more information or from using more sophisticated models. The results show that the majority of performance improvements come from model sophistication rather than from information expansion. In particular, around 77% of the total improvement is explained by moving from simple heuristic rules to more advanced machine learning models, while only 23% comes from adding accounting and equity market variables. It is important to note that these results are based on strict out-of-sample evaluation on the 2021-2023 test period. A more detailed time series cross-validation analysis, which confirms the robustness of these findings across different periods, is conducted and discussed in detail in the return report. Based on these results, several key learnings emerge. First, the results suggest that using more advanced machine learning models is more valuable than simply adding more data. Even with limited information, well-regularized models can extract meaningful signals from CDS spreads. Secondly, parsimonious models using a reduced set of carefully selected features perform almost as well as much larger models, which improves interpretability and robustness. From a practical perspective, this is particularly relevant for early warning systems and credit risk monitoring, where simplicity, stability, and transparency are essential. The detailed robustness checks, cross-validation analysis, and additional analysis supporting these conclusions are presented in the report. So, thank you for listening, and I hope you enjoyed my presentation. Thank you.